Hi class, this is a second example problem for Unit 8.2. Uh, what exactly is 8.2 and 8.3 or 8.1? It's not as clear, that 8.1 or 8.2 or 8.3 are doing exactly, focusing on one principle or the other. It's all related to just friction, slipping, tipping. Um, so whether this problem is more applicable to 8.2 or 8.3, regardless, I thought it was an interesting problem that lets us talk about um, some interesting things. So what we have here, this is problem 823 in the 13th edition of the book, is we have this bar. It's pinned at point B and pinned to a disc at point A. So it's not rigidly attached to this disc, it's pinned at point A. And we have this force P being applied to the bar, and this disc is resting on this slope. And at this point of contact here, the coefficient of friction is 0.2. The disc weighs 35 kilograms, and what we're asked is to find the max force P that can be applied to the bar AB without causing the disc to slip at point C. And we can neglect the bar's mass. So think about how you'd approach this. This one is a little trickier, but if we just use the same fundamental principles of breaking down, each part of our problem, drawing free body diagrams, and just remembering what our basic equations are, then it really turns out to be not all that difficult. So obviously the main, bulk of the problem is going to be about this disk because that's where the friction is applying. But first we're going to start by doing a free body diagram of the bar because we need to figure out, because ultimately we're trying to find P, we need to figure out how does P translate to forces felt on the disk. So I'm going to draw a free body diagram of bar AB. And bar AB has a force By, has a force Bx from that pin. It has this force P, and then there's this pin that is going to give you AY, AX right there. So what we mostly care about, we can obviously just by looking at it, we can say, well, obviously AX is equal to BX. That's not very interesting. But what we really want is we want to figure out how does P get into the system of equations on the disk. So I'm just going to do a simple sum of moments about point B, because really I want to get what is AY in terms of P. That's all I'm really interested in here. How does P, because that's how P is going to make its way into our equations at this free body diagram. So if I do sum of the moments about point B equals 0, then I get P times 600 millimeters, that length, and that's going to be positive by right-hand rule. And then the way I've drawn AY will be negative. So I'll say minus AY times 900. And what that ends up telling me is that AY is equal to 0.6667 P, or 2/3, right, if you prefer. So let's hold on to that. So that's all we really need, all the information we really need out of the free body diagram for the bar. So now let's look at the free body diagram for the disk. And this is much more interesting and kind of complex. So if we have the disk, we have this force AX, and I'm going to draw it in the opposite direction as I did here, and AY. Obviously, we just found AY. And I'm drawing it right, I'm drawing it the opposite direction because the forces are going to be flipped on the other side of that pin, as we've seen before. The disk itself has a weight of 35 times G newtons, and there's going to be a normal force, which we'll call NC, and there's going to be a friction force, which I will call, because we know we're trying to find the weight at the point of slipping, I'm just going to go ahead and call that NC times mu sub S. not even give it its own unique name. And obviously the angle that this guy's acting at is 30 degrees because it's parallel to the slope. The angle this guy's acting at is going to be 60 degrees because it's perpendicular to that slope. And if you want to verify that to yourself using some trig, just to feel confident about that, go ahead. I had to, I'll admit. I often draw little similar triangles and things just to make sure that my angles are correct. So that's our free body diagram. So we got all these forces acting on there. And so we're going to have to do some math here. So the first thing that I'm going to do, I'm going to go ahead and call this middle point of the disk point D. I'm going to go ahead and take the moments about point D because I can get some simple relationships. Just taking that point D cancels out AX, cancels out NC, cancels out the weight, and I'm just left with the friction force in AY. So that gets me a nice relationship there. So I'm going to say sum of the moments about point D, which is what I'm calling the center of my disk, equals 0. And all I'm wound up with, right, the diameter of this disk is 200 millimeters. And because all these are tangential, AY and the friction force are tangential to the disk, I can just use that distance. So I can get NC, and the friction force will cause a positive moment the way I've drawn it. So NC times mu sub S times the moment arm of 200 minus AY times the moment arm of 200. And AY, of course, is just, 2/3 P. And so I can say right away by rearranging this, I can get NC is equal to, I'm skipping some steps of math, I apologize. But I can get NC equals to 3.333 P. So I'm able to solve for NC in terms of P. So that is a big step. And now the other equation, sum of forces in X doesn't really tell me much. It lets me find AX. So if I was interested in finding the reaction force BX or something, I'd do that, but I'm not. I'm interested in finding P. And P, the only other equation where P will appear will be my sum of forces in Y, because I can get P in relation with regards to AY. So I'm going to say find my sum of my forces in Y equals 0, which is, so I get minus 35 times 9.81 minus AY, which again is just 2/3 P. So I'm just skipping straight to that substitution, minus NC mu sub S sine of 30 plus NC sine of 60. So if I sub in, this value for NC here, what I end up getting is 0 equals, so this value here is going to be minus 343.35 pounds from the mass of the disk, minus 2/3 P minus, or plus, minus 1/3 P plus 2.8867 P. And then I can do some rearranging, and I get that 343.55 equals 1.8867 P. And P therefore is equal to 181.98 newtons. So even this problem that looked kind of complicated to start out with really wasn't that complex once you just break it down by the parts and just think about, I have per free body diagram. I have my three equations. What ones tell me the information that I need to get to what am I trying to find? I'm trying to find P. How am I going to find it? My sort of key here is knowing that at the point of slipping, the friction force will be that the normal force times coefficient of static friction. So then you sort of do this working, forward to get the answer that you wanted, or to then bounce backwards again. So hopefully that made some sense. If you have any questions about that or how to think about a problem like that, how you even consider going about that sort of a problem, go ahead and message me or call me or come into my office hours anytime. Be happy to chat. And hopefully you found that useful. Thanks for watching.